Okay, so hello everybody. My name is Bojan and I work for Coinbase Commerce. Today we're going to talk about how we implemented ERC-20 payment acceptance at our platform. So this is kind of like the overall agenda of the talk. First, we're going to talk a little bit about like how crypto payment processors work, why they're important, what kind of like role they serve. We're going to talk a little bit about ERC-20 forwarding and why is it important and how we solved it. And then we're going to go on and focus a little bit on create-to and minimum proxy contracts. These are relatively new additions to the Ethereum virtual machine that we've used, and we thought that we think that they're very cool, and I think that they can be applied into like a wide variety of like use cases that go way beyond payment processing. What is Coinbase Commerce? Well, we try to be the easiest way to accept crypto. We come with like batteries included, meaning that we want to make it like super easy for developers and just like merchants to accept cryptocurrencies. We started 2 years ago, and since then we've developed a lot of integrations with third-party websites like Shopify, WooCommerce. We have like a number of SDKs that developers can use. We have an API. We send like web notifications and a bunch of other stuff that you might need. What makes our product interesting from philosophy, as well as from both from philosophy as well as from like engineering standpoint, is that we're hosted but not custodial. Hosted meaning that you don't need to run any software on your own to use our product. You just like sign up on our website, and like essentially we handle everything for you. But we are non-custodial, meaning that Coinbase Commerce never has access to your private keys. All the transactions are completely peer-to-peer, and everything that happens is like in a truly kind of like distributed manner. We cannot seize funds, we cannot like stop anything. Everything is between the merchant and the customer. When we started with supporting Bitcoin, Ethereum, Litecoin, and Bitcoin Cash. And since then, we supported USDC, and like this talk essentially explains what things we needed to do and how we approached adding USDC. USDC is stablecoin developed by Coinbase. It's implemented as an ERC-20 token, so everything that is here basically can be applied to any other ERC-20 token. That's pretty much like what payment processors do. They kind of like accept payments on behalf of the merchants. They handle all of this stuff, and let's kind of like dive into like what actually happens when a payment occurs. So let's meet like Carol, the customer, and Matt, the merchants, and let's say that Matt wants to sell some bananas to Carol. There are many ways that kind of like this interaction can happen. In the very, very simplest case, you can imagine that Carol just sends some Ether to Matt's account, and Matt will just like give the banana, and that's the end of the story. This thing works in real life, but unfortunately it breaks whenever you have like anything kind of like more scalable, because if soon enough you get into an issue of like you don't know who paid for this particular banana. If Matt shares his only address to everybody, then it would be impossible for him to know. He might need to ask for proof from Carol, either by the transaction hash or something else that transaction occurred. But this thing becomes like very hard and very cumbersome super quickly, and especially if you think that most of the customers that we have today, they come from exchanges and they don't really have like any good way of providing any additional data, like kind of like just like saving simply information does not work. Some of our competitors develop like payment protocols that are very cool, and they solve this issue by making like an RPC call between your kind of like private wallet and essentially the merchant server. But this again like excludes a lot of people that use exchanges, and we want to make our products to be like the easiest and simplest to use by everybody. So our solution essentially includes this widget. This widget here has like two important numbers. The first one is just like the amount that you need to pay for this particular transaction, and the second one is like the more important one is like that address. That is like a uniquely determined address for this particular charge that has never been kind of like, that has never existed on the blockchain before. And it's very important that all of these addresses are unique, because we can definitely know that this address is completely associated with Carol's purchase. if funds land on that address, we know that it must have been Carol that paid for those. So kind of like in a little bit more visual way, like when Carol wants to buy these bananas, we generate a new address for this interaction, 0xbanana. She sends some ether to that address, and while doing so, she pays like some transaction fees. At this point, the interaction is done. Like Coinbase Commerce would send all the appropriate notifications. Matt, the merchant, received those funds, but Matt would kind of like to use these funds. He would like to spend them somehow, and the way that he does that thing is that he signs some transaction originating from like that intermediary address that he controls, and he pays fees for that. This thing works very well for Ethereum, but there is like slight issue that we're gonna get to about ERC-20. We call kind of like these intermediary steps where we generate like these new addresses, like forwarding, because like we're introducing this kind of like hop that needs to be forwarded. And for ERC-20 tokens, we would have the same thing. We have like the unique address for this particular instance, Carol's and some USDC tokens. She pays transaction fees in Ether, and this also works out well. This is kind of like how everything works. But like when Matt wants to withdraw the USDC tokens there, we get to an issue. We need to pay fees in Ethereum because that's like in Ethereum, the way that kind of like these transactions work is that the intermediary address, like this address banana, needs to contain enough ETH to cover for the transaction fees. But because this is like a newly generated address that does not contain anything, it's essentially impossible. This does not work. And there are a couple of ways to kind of like go around this thing. And the very simplest thing is that, well, maybe we don't really need this intermediary thing, and maybe just like Carol can call the proof from function, and that solves all of our issues. But then again, Carol cannot use any exchange or any kind of like simple wallet. It requires specific like Web3 compatible wallet for that kind of transaction. For that was just like a non-starter for us. Another thing is that maybe Matt can just like deposit a little bit of ETH at that intermediary address that would be used to cover for the transaction fees. But this also becomes like super tricky to implement like super fast because the transaction cost is like variable. We don't know the actual gas amount that will need to be spent, as well as the gas price in Ethereum is like subject to essentially market conditions. So it's like super hard to figure that out.
Are you going to be wrapping up soon? Just let you know.
We just started.
We just started.
Yeah.
So that kind of like puts us in like this tricky situation where on one side we need like these like address-based systems, but we kind of like also need Ether on those addresses that we cannot find. Thankfully, Ethereum lets us create contracts, and we can use like smart contracts to like solve this thing. This is like a 10-line or so smart contract that is essentially the base of our solution of how we do that thing. When we initialize this forwarder contract, we get like a destination that's like that's like the merchant's final destination that they want the funds sent to. And the only thing that this contract can do, it has like just like single function, flash tokens, that can be called by anybody. And whenever that function is called, the funds automatically get transferred from like this intermediary address to the final destination. Something to be kind of like noted that we'll get back a little bit later is that this flash tokens function is completely open to anybody. There is no guard by owner only or anything like that. It's like freely available to like everybody to call. So if we kind of like go back to our diagram, now we have like Carol that wants to buy the bananas at the unique address, but now it's not like just like a simple address, it's like a smart contract that's initialized with Matt's final destination. She sends the USDC tokens to that address, and whenever Matt wants to withdraw the funds, instead of like him sending some Ether, anybody in the world, whether it's him, whether it's Coinbase, whether it's like any other third party, would call this flash function. And whenever this flash function gets called, the USDC automatically gets transferred to Matt's address. And I do hope that at this point you can kind of like see how these forwarders solve our problem. We could essentially deploy a bunch of these forwarders whenever somebody pays, we could call the flush function, and essentially the funds would go wherever they need to go. So this is all good. Like the good things about like this solution is that it's like address-based, so anybody could pay from whether they have like a mobile wallet, whether they have like Web3 compatible, or they're just using an exchange. It's completely non-custodial because like anybody can access these contracts, and nobody could prevent the funds reaching their final destination. And we don't really need any ETH in the account itself to like handle these payments, which is all pretty good. The bad thing about these contracts is that like it's a lot of repetitive. It's like very hard to deploy because the way that what we've described so far, we would need to deploy this pool of contracts beforehand. We don't know how many we need to deploy. They are all costly. It's all like expensive to manage. So if you try to kind of like deploy this thing at scale in like real life, it's becoming like very like super soon. So what are we gonna focus on like for the rest of this talk is kind of like the patterns and strategies that we've used to kind of like mitigate the bad sides. And all of those things are something that I think is like very readily applicable to like any other to a lot of other situations. Any situation that has this kind of like simple repetitive things that you need to do, that you need to kind of like do them on a per session or per user or something based, could benefit from these patterns. The first thing that people can do to kind of like mitigate the cost and the complexity of this thing is to use a factory. A factory is essentially a singleton contract that's deployed once that contains the logic of the contract and knows how to generate new contracts. So this is like the forwarder factory. Over here, like we just like have like an init forwarder function that can deploy a new forwarder. Once we have like this factory in the blockchain, we go from something. This is like over here we are seeing the raw transaction that essentially deploys a forwarder. So the code over here contains all the logic of like how the forwarder is being initialized, what does it mean to like flush. All of those things, that's like a lot of logic. Compare that thing with like these like couple of lines down there that only contain essentially this thing says like, hey, like like I have this singleton factory on the blockchain, call it and call the init function. Both of these functions perform the same logic. At the end of the day, either one of them will end up with a new forwarder being deployed on the blockchain, and they are kind of like indistinguishable, like functionally speaking, from one another. But essentially the EVM rewards us for using less space. In the first case, like we have like 1.7 kilobyte weight of the transaction, and we use like 440K of gas, and we've reduced that to like less than 200 bytes of data with like 240,000 units of gas. So this is like pretty significant savings that kind of like it's good, but we still have like problems with it. How many of you know how essentially like addresses are calculated in the Ethereum blockchain? It's like a little bit of a mess, but pretty much we have the original way that like when you deploy an address, essentially you take some hashing function of the parent address and like a number known as nonce. The nonce is like an ever-increasing counter associated with the parent's account of like how many transactions have originated from that thing. And this essentially means that there is like a global state, a serializable state of kind of like like accounts that of like transactions going from here. And it's very hard to build production systems that depend on nonce. It's very easy to get something wrong. It's very easy to create a transaction with like something that's invalid there, that's like has like too low of a gas, that makes the whole kind of like it makes depending on future addresses like very hard. But thankfully, with the latest Ethereum fork that happened like earlier this year, we have something that's called Crate2. And Crate2 removes this essentially implicit global dependency on the nonce for something that's like very explicit. Now we pass in a salt that is kind of like determined by the developer. and also like there is the code, but like that's like slightly less important. What this means in kind of like real life, like so like in very kind of like technical terms, these are the changes that we need to do to start using Create 2. So you can see that like in the first line, you cannot like really see it, but like in the first line, we are passing an explicit sole parameter. Before that, its function was like performed by the implicit nonce. And then the other two changes is that instead of create, we use create 2, and instead of like the implicit nonce that was not passed, now we pass the sole to the create 2 function. This is a huge win in terms of operational reliability and just kind of like security and having like some trust in the code is doing the right things. Is because like right now we as like the users of this factory can know where these forwarders will be deployed without really knowing the state of the blockchain, without really knowing like how many contracts have been deployed from this factory, without having to have like any guards in this thing. This allows us to essentially simulate a lot of. This essentially like gives us the possibility that we can calculate these addresses, forwarding addresses a priori, without deploying them to the blockchain. We can show them to the final customers, to the people like Carol. Carol can pay to that address, and only after she has paid, we can then deploy the contracts, and we are certain that they'll be deployed at the right address. We are certain that nothing bad can happen with that. So it's a huge win for any kind of like DF developer or like hardware wallets or something that does not need to constantly interact with the blockchain and know its state.
And if she never pays, you never have to deploy the contract.
Yes, and also like there is like a very security kind of like whenever you interact with these things, you want to have like a symmetry between how much it costs for an attacker to essentially deplete your funds or deplete the merchant funds, and how much you can kind of like you need to spend. So this one aligns those two things well together, because if you need to like eagerly deploy contracts on the blockchain, then it's very easy for somebody to just like deplete the merchant's funds by creating thousands of contracts and never paying any one of them. But with this scenario, they need to incur cost on their own. They need to first pay something on the blockchain before it's actually used. So it's like very, very good stuff. The other thing that we've done to make this thing a reality and to make this thing like usable at like kind of like production scale is we use like what's called minimal proxy contracts, which is like a very, very, very cool feature that allows to go from like a transaction of this size to transaction that goes of like that size. What we see in the code below is like a huge, huge, huge reduction, both like in bytes as well as like in gas. Essentially like the transaction below is deploys a contract that you can think of like a symlink to any other contract on the blockchain. So the transaction below, this is like, I don't expect like you to understand or to read this thing, but like this is like everything that it does is like it deploys like new contracts that gets initialized with like a single address, and any call to these like very, very small tiny proxy contracts would get like this kind of like like relayed and executed by the other one. This is probably like the smallest contract that can exist on the blockchain, because it just kind of like says like, hey, like like I was called with something, I don't know what it is, but I do know that like my parent can answer this question. So we use this thing to essentially come up to this topology of our contract. So this is like how our system works today in production. We have like a single forwarder factory that knows how to produce these things. It has like a fixed address, it's a singleton that we've deployed once and we can forget about it. And whenever a merchant comes, we deploy a forwarder with their final destination. And from that point onwards, for any interaction with like any of their customers, with any Carols out there, we calculate a clone address. Whenever Claire would deploy, would paint one of those addresses, only then we go and like we actually like deploy that clone. And that clone doesn't know anything. It just says, hey, like like I don't know about anything, but I know that like my forwarding parent knows about it. So it would just like essentially before the implementation of the forwarder knows that, yeah, I just like need to send the funds to destination, and that's kind of like how it goes, and how it goes. So like, yeah, like overall, like what we've done here is that we developed like these smart contracts that are like easy to use for anybody, regardless. They don't require Web3 support. They're non-custodial. Like anybody could, even if right now we manage all of this contract deployment, but that's not like any strict requirement. The merchant can themselves code these contracts. They're completely open. Anybody could code these contracts and like flash the funds. And we've solved the repetition problem. Like what we deploy is like super minimal. It's like very reliably to kind of like compute these addresses. We can be certain that we cannot have any bugs in terms of like nonce calculation or nonce management, and they're like relatively cheap to deploy. Especially if you consider that we can reuse these contracts. So once we don't do this thing today, but I'm pretty sure that we will. Once this thing becomes like a bottleneck, we could like reuse the contracts that we have, and from that point onwards, it becomes like as cheap as just like kind of like calling like the transfer function. It's like virtually free. So that's pretty much everything about what we could have, like what we had. We can kind of like have questions if you guys want about any of this stuff. Yeah.
When you create the flush contract, send it forwards to where the address that you're flushing it to, what is the address that it flushes to? Like, where is that?
So you can think that that's like the merchant's final destination. Right now, we deposit to kind of like the merchant's default Ethereum address based on their like kind of like BIP32 seed. So that they could kind of like import their seed in, like from like some like any other like third-party wallet and see all of their balance. But you could imagine that that destination can be like a setting, like determined like somewhere in like the dashboard in the settings. So it can be like an exchange or something. So like the funds will automatically like flow there.
Is that currently a thing? Yeah.
It's not currently a thing, primarily from like UX perspective, because if you put your kind of like exchange address there, it would be very hard to kind of like tell you like what's your balance, of how much money you've received, what does it mean to withdraw those funds. Like it gets like very tricky very fast from like UX perspective and product perspective. But technically there is nothing preventing that thing from happening.
Have you thought about self-destructing the contract after you forward the gap?
Yep. Yeah, so self-destructing the contract will reduce by, I think, 15K the gas cost.
Okay.
And that's definitely something.
And with Create 2, you can actually recreate the contract at that address if you need to again.
That's true. Something that's a little bit tricky with Create 2, and especially with minimal proxy contract, is that there is like a weird dependency on, like, it introduces a lot of, if you want to make this thing completely open, if you want to make this thing kind of like very simple to use, it gets like very tricky very fast, at not enough cost benefit. Like
Sure.
the money that you get back.
Yeah, I mean, if it's only 15K gas, that's not.
Yeah, that's like one reason. The other reason is that I do think that we'll get to a point where we can have like this pool of addresses that have been paid to, and because these are kind of like one-time things, like like if a customer pays to the merchant, we need to monitor that address for like a while, for like a week, just like to make sure that somebody doesn't pay something twice or something similar. But after that, we can reuse that address for like another interaction.
Right.
And in that case, that
You're
is
not
free for
saying
us.
that, right.
Yeah.
If you can do USDC, that means you can do pretty much any ERC-20.
Yeah.
Is the UI just not there yet? But right now it's limited to, or is it only going to be things that you guys list?
technically, we could, on the technical side, we could support any ERC-20 token. There is like literally no limitation.
Right.
It's like adding like one line of code somewhere to say like monitor this token. It's like a product question at this point.
It's definitely part of the UX. I think it's partly also just adoption of the ERC-20 tokens that we would add. I think there's still a little bit of a gap on users adopting this technology because they still need to have ETH to be able to then pay with it. So it just generally has that hurdle. But if you start seeing more adoption of just general like USDC or other ERC-20 tokens, then we probably we prioritize adding more.
I see this as a really good UI if it could just fund DAOs for me to just make users more comfortable making that transaction.
Yeah. And at the end of the day, like you're more than free to like use the contracts and like if you end up the destination being the DAO contract, you'll automatically get flashed and you know like who paid for what. You can have like that stuff. You cannot do that thing from like the product itself, but you're more than welcome to use like the contracts to do that on your own. Yeah, I mean, I guess like we're running a little bit late on time, so don't have any questions, but we can